Before looking at individual AMBA protocols, it helps to start with why the family exists at all. AMBA is about system integration discipline. It gives chip teams a shared contract for how blocks issue requests, return data, complete transactions, and handle timing. Without that contract, each interface boundary becomes custom translation logic and custom verification work. The result is slower integration, higher risk, and less reusable IP. AMBA reduces that friction by defining common protocol families with clear behavioral rules. The original pain point was simple. SOCs combined many blocks, but each block boundary could use a different private interface. That forced teams to keep writing wrappers, bridges, and timing exceptions. Verification environments had to rediscover similar bugs again and again. It also limited performance scaling, because one internal bus pattern had to satisfy very different traffic types. AMBA addressed this by defining protocol families that are interoperable and purpose-fit instead of ad hoc. AMBA is not only about naming wires. It standardizes how transfers happen and what a transaction means. That includes flow control discipline, burst and data behavior, response semantics, ordering expectations, and protection qualifiers. Because these rules are explicit, teams can design and verify reusable components with predictable integration behavior. That is the core engineering value. The protocol itself becomes a stable contract between independently developed IP blocks. Another key design choice is that AMBA is a protocol family, not a single universal bus. Control register traffic, high-throughput memory traffic, streaming data paths, coherent fabrics, and chip-to-chip links have different constraints. Trying to force one protocol shape across all of them would either add unnecessary complexity or block needed performance features. AMBA keeps consistent architectural principles while allowing each protocol to optimize for its traffic class. The benefit is not isolated to hardware designers. Verification engineers gain reusable compliance infrastructure. Firmware engineers see more predictable device and memory interactions. Platform teams can evolve interconnect and bridge strategy while preserving endpoint compatibility. In practice, AMBA shifts effort away from repeated interface firefighting and towards system-level optimization. The shortest summary is this. AMBA exists to make large SoC integration tractable. It replaces private interface agreements with stable protocol contracts, and it does so using a family model that supports different traffic types. That is why AMBA persisted from early AMBA 2 material through modern AMBA 5 protocols. It solves a durable engineering problem, not just a historical one. If this foundation view was useful, like and subscribe to be notified of future videos. The next parts of the series move into why AMBA 2, 3, 4, and 5 exist, how the protocol families evolved, and then the latest version overview, RTL-focused, and firmware-focused cuts for each major standard. To close, here is a short glossary for the acronyms used in this video. AMBA stands for Advanced Microcontroller Bus Architecture. IP means an intellectual property block, such as a processor, bridge, or peripheral integrated into the chip. SoC means System on Chip, which is the complete integrated device that brings those blocks together. Two other terms appeared in the Team Impact slide. RTL means Register Transfer Level, the hardware design abstraction used to describe and verify digital logic. MMIO means Memory Mapped Input-Output, where software reads and writes peripheral registers through ordinary addresses.